3D printed structure, which was borrowed from someone else's project. Here on the right, you see a couple of 3D printed parts that were discarded due to defects and couldn't be used. Um, the example of the files from which the 3D printed parts have been generated, the metal joints, nuts and bolts that keep everything together, a bone black development board running a headless IoT version of Debian, a industrial webcam module for video capturing, and 3 servo motors for moving the arms of the structure. So, brief overview of the PID theory functionality. So we have a plant, which is a system we wish to control. A command is given to a controller. A control signal drive is generated and applied to the plant. The plant responds with a behavior which is measured and fed back into the controller. The feedback received and the command would give the next drive signal to be applied to the plant. But what is the new drive signal after the feedback? So first of all, let's take a look at the concept of error in the system. So the error is the delta between the current state of the system versus the desired state, the target, or the equilibrium point. So the signal to be fed back into the system will be a summation of these 3 different type of error, so to call it. Will be the proportional controller, which is the gain in the system, which is the error signal multiplied by a constant Kp. We can think about it as a correction in magnitude. If we had the correct direction but smaller magnitude, we will approach the target very slow, whereas a higher magnitude, like higher than needed, would overshoot the target, the optimal point. The integral controller, which is the sum of error over time, and this allows us to remove the constant error in the system, and derivative, which is the rate of change of error that allows us to predict the future values based on the current rate of the error. So for our system, the equilibrium point will be the center of the plate where the ball doesn't move, and the error will be the difference between the current position C and the target position T. So the signal, the new signal to be fed into the system, will be the sum of these 3 errors, which are continuously updated and calculated for in both direction, X and Y. So we'll have to calculate the sum of Sx and Sy for the error, the error rate, and the error so far in the system. So I won't go into the math here, but just a brief description. So in order to bring the ball to an equilibrium point, we'll have to move the plate, basically change its angle of inclination. So we define a vector v, whose projection form a 90 degrees angle with a vector v. While changing the plane inclination of the plate, the angles alpha, theta, and beta will change relative to the x, y, and z axis. So basically, we can define the inclination of the plate based on the angles between the x, y, z axis and the vector v, and the distance between the current position of the ball and the target position, which will be 90 degrees angle with the SX and SY sides of the triangle. So after we define the angles that we need to find, we need to the desired angle. In order to move the plate, we will have to move the servo of the servo motors in order to move the plate. So we can actually determine what angle theta the servo needs to move in order to generate the alpha, beta, and theta angles needed for the plate in order to bring the ball closer to the equilibrium point. So this will be the derived formula. I won't go into, it's beyond the point of this presentation, but put it down here. So the BeagleBone and the programmable real-time unit. This was kind of difficult, actually. I didn't expect it to be this hard. So the BeagleBone AM65 SoC has two real-time 32-bit 200 megahertz RISC cores. They both have 8 kilobits of data memory and 8 kilobits of instruction memory. They can use their own memory, allocation, but they can also share memory with a host device. They provide support for interface applications that have hard real-time constraint. This project I used to manipulate input-output control servos through PWM. So the SoC is run via the Linux remote process framework, which is designed to allow a main processor that is running Linux to control slave processor via operating system device binding using C, basic C, and assembly. So basically, we would bind a process to a PRU. So PRUs are not configured, require some type of a firmware file that needs to be uploaded to PRU at runtime. The Linux remote processors allows kernel to communicate with processor using communication channels. It bounds remote processes to PRUs, and GPIOs must be configured in the PRU cores. Special compiler is needed, and also there's a linker for linking the PRU register to the main processor, some type of mapping. So OpenCV, so we use the OpenCV API to detect and track the ball movement. Um, Everything worked okay with the tracking part. So current status of the project. So the OpenCV detects the object in the frame and passes the object position value to the program. The program computes the beta, alpha, theta needed to reach the target position. I have also tested this manually, with, inputting manually the angles, and it works correctly. The board outputs a PWM signal uh, to adjust the theta angle of the servo uh, accordingly, and presumably correct values. Apparently, there's no way that I can check the PRU's output unless connected to a oscilloscope. The servos receive an input value from the board because they, you know, they move, but unfortunately not uniformly, and the structure sometimes it gets stuck. Actually, probably most of the time gets stuck. So it's either a structural issue or something that is wrong with the PRU implementation. I'm not 100% sure. I'm still investigating that. So conclusion. So physical design structure was very well put together by the original designer, creator, but the design gives very little room for error compared to other designs. Execution of the initial part went relatively well, except for the programming and testing of the PRUs. Challenges. The initial set of the 3D printed parts were discarded since the surfaces were very rough and would create a lot of friction in the system. Programming the board real cores requires a special code generation tool, manipulation of the register, and writing firmware file or modifying the firmware file for the initial setup of the PRUs. I found out that the board cannot use HDMI output, so I cannot look at it on the screen. Cannot see the output of the camera while using the PRU cores. So there's no video feedback available, and needed to use the X1140 or VNC. So for future work, running OpenCV and the program on a PC while using a separate board just for the movement control would simplify things. But this project, I wanted this project to focus on the heterogeneous, multiprocessing, where use one board with two processors to do the processing of the video processing and the movement. So the future attempts will be made to solve this problem, and still trying out the BeagleBone board. Also, since the possible positions of the ball are known, at least like a lookup table of pre-computed values that maps the plate angles to the servo values can be created and just read during the execution rather than constantly computing the angles. And probably that would help with the computation. Thank you.